Okay, so if there are no questions, let's start. So we were talking about all of this theoretical analysis of algorithms last time, and before we jump into this, how to use this theorem, we proved this theorem last time. I just want to give you a sense of what we are trying to do with some more experimental analysis. All right. So remember, what we were trying to do was trying to figure out how much training data do we need to reliably learn, right? If assuming that we are working with certain hypothesis space, because our goal is to identify what is the complexity of a hypothesis space, right? And the idea is that any algorithm that uses that hypothesis space, by this analysis we can also understand what is the complexity related to that algorithm, right? So for example, we know that perceptrons work with the hypothesis space of straight lines. So if with this analysis we can understand how much training data do we need to learn a reliable solution, then we can essentially answer the question, how much data do we need for a perceptron to learn a reliable solution, right? And then we talked about how to define a reliable solution, and the point was that trying to find a solution which makes no errors ever, like if it's trying to come up with a solution that makes zero errors is very hard, okay, and trying to come up with bounds for those kind of solutions is almost impossible. So what was done in the past was there was this notion of pack model, pack learnability, where we said that instead of trying to figure out the zero error solutions, let's try to relax it and say we want to find solutions that work, with an error. We are okay to accommodate an error of epsilon. So if I give a new test data point with a probability epsilon, it can make a mistake. With a probability 1 minus epsilon, it will be correct, right? So we are okay with those kind of learners, and we are also okay to learn those kind of solutions 1 minus delta times. So we don't want we don't expect our algorithm to learn that kind of solution which makes only 1 minus which makes only epsilon mistakes for every training data set. We want that to happen maybe we are okay in accommodating a failure rate of delta. So we introduced two terms here, delta and epsilon, right? So let me sort of give you a general idea with some data, right? So let's say this is our data, okay, this is all of our data that is being generated by some distribution. In fact, if you look at this data set, I mean how I generated using a uniform random distribution. It essentially creates a box and picks points uniformly, right? So our data is in this two-dimensional space, and now what we will try to do here is we'll say, let's say our hypothesis belongs to this hypothesis space is all lines, okay? So we'll take any line, right? So we'll pick any line, and you can look at the code to see how I use a line, but idea is that we draw a line and then we split our data into two parts. So I can draw another line, right? I can change my W here. Instead of this, I can make it 3.5 and minus 3, and my line will be slightly different, right? So the idea is that any concept, any hypothesis that belongs to this space of straight lines can be used, all right? So let's say this is our stuff. In fact, right. So let's say this is the one, but the idea is that your algorithm should be able to learn with any concept that is picked from this hypothesis space, because all of them will be lines. So let's say this is that, right? So now what we do is we sample a training data, right? And then we run our algorithm which uses that hypothesis space. So here I'm using perceptron, I'm using sklearn's perceptron library. What? FR. All right. So I learned my perceptron. Of course, perceptron, in this case, I have ensured that the data is linearly separable. So what that means is that your concept C belongs to the hypothesis space, which means that perceptron will learn a line which will make zero training mistakes, right? So it's a consistent learner, but of course it might make some mistakes on the test data, right? So this is what we call epsilon. So because this is, this divided by 962. So 5 divided by 962 is our error, true error, right? So we want to put a bound on that, right? And then what we want to do is we want to say every time I pick some data, I want my algorithm to learn such that it always makes less than 5 mistakes. Let's say 5 by 962 is my epsilon, right? So the idea is that every time we pick a new training data, the concept is fixed, of course, and every time it learns something. Now this time, actually, this time it didn't do well on this as well. But this time it makes more mistakes, right? Next time, it might make more mistakes, right? So every time its value is changing. What we want to do is we want to find the probability that the number of mistakes here are always less than some epsilon, okay? Plus we also want to relax something, that maybe this might not happen every time, but we want this to happen at least 1 minus delta times. So the idea is that if you run this, what I did here, if you run this 100 times, and every time you see, was my error over whatever the epsilon value was, let's say 5, right? And so that will be your number of failures. So, and then you count how many times you failed out of 100, and that's your delta, right? So in this analysis that we were doing last time and we'll continue today, we want to find how much training data do I need here so that I only make more than epsilon mistakes 1 minus delta times. Delta times. You see what I mean? So failure is defined how many times you find a bad algorithm or bad solution. So you want to fail only a few times, right? So the idea is we want to put, so for example, if I had taken more data here, right? So if I had taken 300 data points, what you will see there is that you will make fewer mistakes. So every time I change my data, but I keep the numbers same, my m same, you'll make, well, actually this is maybe too good. All right, so this time it made 4, right? So what will happen is that for larger m, it will happen very rarely that you will learn a bad learner, right? So what we want to find is what is that sweet spot, what is that value of m at which you can make these guarantees that you would not make more than epsilon mistake more than delta times, right? So that is the idea. Why? Because we want to put a bound on m, right? We don't want to use too much training data. Training data is always expensive. Somebody has to label it for you, right? So you want to work with minimum amount of training data that you need, okay? Any questions? Okay, so let's get back to our analysis, which is fascinating, which is here. The idea is that we first proved this theorem, and we almost proved it. There was one error that I made about the probabilities, but I think I made a post in Piazza, so just check that. I will not go into this again. But the idea is that if you have some hypothesis space H, right, and you want to find the probability that the version space is not epsilon exhausted. What does that mean? Epsilon exhausted means that a version space is epsilon exhausted if every hypothesis in the version space. Now remember, what is the definition of a version space? It is all hypotheses which make zero error on training data, but there is no guarantee on how many errors will they make on the test data, right? So if every hypothesis inside the version space makes less than epsilon error on test data, then we call that version space epsilon exhausted. Why is that important? That is important because your algorithm will try to find a hypothesis from the version space, right? Because it's a consistent learner. And if any hypothesis in that version space is bad, then there is a chance that your algorithm will learn that bad hypothesis, right? So we want to find the probability that this version space is good. It does not contain any poor hypothesis. And if that is true, then of course the probability that your learner will find a good hypothesis is 1, right? So what we did was we first said, okay, what is the probability that version space is not epsilon exhausted? That is always bounded by this value, okay? It will be less than size of your h natural exponent e raised to power minus epsilon m. So it is a function of the number of training data points and your epsilon, right? So this is the probability. So now what we want to do is say, so we said that probability that version space Vs is not epsilon exhausted is bounded by this number, size of a hypothesis space, okay? Which means that now what we want to do is we want to bound this probability, right? Because this is also the probability that you will fail. Your algorithm will fail if this happens, right? So which means that we want this probability PR of this Vs not epsilon exhausted, right, to be less than equal to some delta. We want this to be bounded by delta, okay, which means that we would like to bound our this higher bound. So make sure I don't mess up the notation, right? Which means we implies that we want our this probability to be less than equal to delta, right? So we want this. So now what we want is how much m do we need? Yes. Here? Up here? I'll just get to that. Ensure that. Right, see, this is the discussion we had last time where I made a slight mistake. See, remember, probability that version space is not epsilon exhausted, remember, it was not the summation of the individual probabilities. It would be bound, it will always be less than equal to the individual sum of individual probabilities, because remember, I think you made the point that they are not mutually exhaustive, right? So we might be overcounting the intersection, right? But it would always be less than equal to the sum. Right. So what we did last time was, just a recap, was we said that let's assume there are k hypotheses that are bad, right? And we said what is the probability that h1 will be, or it's any hi will be in version space, right? And that was, we said, was 1 minus epsilon raised to power m, because to be in version space it has to make 0 mistakes on those m training examples, right? Then we said, okay, what is the total probability that any of them will be in Vs, right? And it won't be just the sum of these, it will be less than equal to the sum of these, because we can't guarantee that they can be added up. So that was the idea. That's why we have this bound over here. Right. So we I'm sorry, I didn't get that question. Right. Oh, I see, I see. I might have messed up something here. Just give me a second, I want to. Right. I mean, it's not coming from this. What I'm saying is that this is the probability that you could make a mistake, right? And this is bounded by this, that it will be less than equal to this whole value. Now, what we want to do is we want to make sure that we want to find the delta that bounds this probability itself. So it doesn't come from this. All I'm saying is that there is some probability here, and this is bounded by this probability. Now we want to find delta which can bound the upper bound itself, so that it's guaranteed that it will bound the lower bound. So it's not coming from there that way, but so the idea is we want to bound this bound itself, and so we want to find the m that will guarantee that. So all we do is we take a log on both sides, right? So we take a natural log on both sides, right? Is that right? And then this comes here, so minus log of this delta greater than equal to epsilon m, brought it here, right? And this I'm going to just I want to work with positive values, so I'll make this 1 over delta less than equal to m, right? And then this can go here, so essentially at the end you can say that m has to be greater than equal to 1 over epsilon times so this is the result that I showed you in last class as well, is that if you want to guarantee that your algorithm will always, if you want the probability for it to fail to be bounded by delta, where the failure is bounded by epsilon, right, then m has to be greater than this value, right? So if you look at it, it is a function of epsilon, which is how much error are you ready to accommodate. It is a function of the size of your hypothesis space and your function of your delta, right? So if epsilon changes, if I make my epsilon larger, what will happen? See, if I make my epsilon larger, which means that I'm ready to accommodate more mistakes, right? So in our example, it's okay to really misclassify things in every run, then the number of points that you will need will go down, right? Because if you want to learn a crappy learner, you will need less data. But if you keep this epsilon to be very small, that means I'm not ready to accommodate any very less error, I'm ready to accommodate only very less error, then you will need more training data. So that is the idea, right? It's intuitive, but mathematically you can come up to that as well, like that. And the same thing with delta as well. Like if you don't want to fail too many times, then delta will be small, this value will be large, that means your m will become larger, right? Now the thing that I want you to focus on is on this, right? What you see is that this m is a function of the size of a hypothesis space. So if your hypothesis space is very complicated, I mean very large, then the data that you need to learn a reliable packed learner is going to be larger, right? So for example, if you remember conjunctive space, right, conjunctive hypothesis for a d-dimensional data, the size was 3 to d plus 1, right? Is that, I think that was there, which means that you can now compute m like that, right? But if you remember our agnostic or unbiased learner, which says that I'm not going to make any hypothesis assumption at all, the h was for binary data with d attributes was 2 power d, right? Which means that you will feed that here and then m will be larger, right? So the idea is that as your hypothesis space grows, the amount of training data that you will need will also increase, right? So this result helps you understand the complexity of your hypothesis space, and in turn it helps you understand the complexity of any algorithm that works with that hypothesis space. So for example, somebody asks you, hey, what would be, how much data would I need if I have candidate elimination, right? Use this. But if somebody asks you how much would winnow take, right, then you will have to feed in the appropriate size of your hypothesis space. So it will be different. So this is one way to understand the relative complexity of different hypothesis space in terms of m. How much data do you need? Okay, any questions? Okay, so one thing that you can do with this is, I'll just give you an example here, is right, so you can do all of that. So essentially if I give you a question saying how much data do I need if my epsilon is 10%, my delta is 5%, and this is the size of my hypothesis space, then you just feed those things here and you get your answer, right? So for example, Let's say somebody, a salesperson comes to your house, hands you a flyer selling you a machine learning algorithm, right? That happens all the time. And let's say the person says, hey, here is an algorithm, right? And it learns conjunctive concepts in polynomial time, and it gives zero training error. And it is excellent because it always creates a great model, which is less than 10% true error rate 95% of the time. And then it makes a claim that you can do that using as low as 200 training examples, right? So you can verify this claim by using this result, okay? Because you know what epsilon is according to this advertisement. You know what epsilon is over here. You know what delta is. It will be 5%, right? And you know what m they are claiming to be. So you can compute your m and see if it is 200, less than 200 or not, and then you can sort of check, right, and save yourself $1,000 by not buying a unverified algorithm. All right, any questions so far? Okay, now one thing that you will see in this ad, as well as what I was talking earlier, is that we always assume that your concept is in your hypothesis space. Okay, that's why it learns a consistent hypothesis, which makes zero training error, right? But what happens if that is not true, right? For example, in neural networks, in the other perceptron we see, they can work even if your C is not in H. Maybe there is no line to learn, but they can learn the approximate hypothesis, the best enough, or good enough one, right? In that case, what happens is, so if somebody comes with a new ad, now you cannot apply the same result from here, because here that thing has changed, that assumption that C is not in H, right? So it turns out that there are bounds for that situation as well. When C is not in H, we will not go into that derivation in this class. It's there in Tom Mitchell's book if you are interested. But what happens, it has a very similar expression, except that instead of epsilon, it is epsilon square. Okay, so that's it. Otherwise, I mean, the derivation kind of follows what we did earlier. It just makes one use of Chernoff inequality to allow for C to not be in H. Okay, but for this class, let's not worry about it. I'm just showing this to you because just for the sake of completion. All right. Any questions so far? All right. Now comes the next interesting question: is what if our hypothesis space is not finite, which means that we can't put, what if this size is infinity, which is true for perceptrons, neural networks, right? Because you can have infinite lines for a perceptron, right? Can we get a bound like this in that case, right? Of course, we can't use this result anymore. Even if we allow C to be not in H, even then we can't get this bound because H is going to be infinity in that case, right? So the interesting question that comes now is, how can we define the complexity of a hypothesis space when it is, or the size of a hypothesis space when its actual size is infinity, right? And that is where we come with this notion of how to handle infinite hypothesis spaces, all right? So I'm going to introduce this notion of what we call Vapnik-Chervonenkis dimension, all right? Or VC dimension. From now on, we can call it VC dimension. There are incidentally also my initials, but these were two very famous Russian mathematicians, computer scientists. Of course, Vapnik now lives in New Jersey, but they came up with this way of defining the size of a hypothesis space when the actual size is infinity. Okay, and they call it VC dimension. So think of it as like a measurement. So you take a hypothesis space and VC dimension will give you a number which kind of can be replaced. You can use that instead of H. Okay, and then you can get your bounds. So we can replace this there and get our bounds. Okay, so that's the idea. So now how do we define this VC dimension? Right? So VC dimension, to understand VC dimension, first we need to understand something else, right? So let's say we have a hypothesis space, right? This bag over here with lots of hypotheses inside. Now what is the effect of every hypothesis on some data, right? Every hypothesis, if you give it some data, it will partition it into two classes, right? We are still assuming these are binary classifiers. So it will call some of the points in this data positive and some negative, right? That's the effect. Now, of course, if I give some training data, some data, so let's say I have some data set S, which is a subset of all of your data, we can partition that data into in how many ways? Two powers S ways, size of S, right? Because I can color everything red, I color everything blue, and then you know the story. I've said it many times. But the idea is that you can partition a set S in many ways, which is 2 power S ways. Now the question that VC dimension asks is that is there a hypothesis in this big bag that will also color every possibility in one way? So I mean, let me try to explain it in a slightly different way. So let's say we are dealing with lines, right? Let's say our H is lines. Assume H is a set of lines. This is the hypothesis space, right? And let's say our S and X, this X is defined in two-dimensional space. So there are two features. And let's say I have S has 4 points, okay? So 1 point is over here, 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 right? So this is my S subset of all your points. Now I can color it or I can label it in two, this can be labeled in 2 power 4 ways, right? I can call all of them, let's say positive, negative, call all of them positive, all of them negative, and so on, right? What VC dimension wants to ask is that will there be a hypothesis in H that will have the same effect? So let's say I color everything positive. Will there be an H that can color, that can be drawn, because these are lines, which will call all of these positive? And the answer is yes, right? You can draw this line. It will label everything positive. So this is good. Let's say I take another, so this is the same data set, same sample, but I color it like this. Now, is there a line in H that is going to be able to classify it in the same way? The answer is yes. At least there's one line. There could be many lines, of course. Then there could be another, right? And let's say I color it like this. Now is there a line that I can pick up from this H which can be used to classify them perfectly? The answer is no, right? You can never draw a line such that all positive are one side, all negative are one side. So no, right? Or a big no over here. Which means, so what this means is, so the direction I'm trying to go is that VC dimension tries to see what is the largest sample size such that we can do this. And that would define the complexity, that VC dimension, right? So for example, instead of S to be 4, consider S to be 3. So there are only 3 data points, right? So you will have at least one sample, let's say like this. Now this sample, however you color it, this sample can be, this can be labeled in 2 power 3 ways, right? If you go home and try it out, however you label it, you will always be able to draw a line, right? So it seems like 3 is okay, but 4 is not, right? So that gives you a sense of, now if you have any other hypothesis space, for example, let's say you have a hypothesis space that contains all of your neural networks, like all of your weights in a one single hidden layer neural network, then you can test how many data points can I draw such that I could find a neural network that would be able to classify it, right? So that is the idea. We call this, in this analysis, we call this the notion of shattering, okay? So if you are given a set of instances S, which is a subset of your data space X, then we say that a hypothesis space shatters S if there is at least one H in this hypothesis space that can represent it. When I say represent, essentially it has the same effect as whatever the partitioning is. So when I say partitioning, it means coloring, right? So if you can come up with a hypothesis which belongs to the hypothesis space which will have the same effect as that coloring, and if that can be true for every possible coloring, then we say that H shatters S, right? So if I can draw my hypothesis like these, right? So for example, these are the all possible ways I can color it, right? I can either call nothing as positive, I can call everything as positive, I can call two of these, two of these, two of these, or one of these each, right? So these are the all possible ways I can partition it. Any hypothesis space will shatter this S, this particular S, this subset, if there is one hypothesis space, one hypothesis in this hypothesis space that has the same effect as this partitioning. All right? Any questions with that? There will be a couple of gradients problems to sort of bring home the point as well. Okay? So let's look at some examples. So let us say that our data is represented in this one-dimensional space. Okay? So every data point has only one feature. That means that you can put it on a number line, right? And let's say our hypothesis space is defined as intervals on this line. Okay, so any hypothesis space can be defined as two values on this number line. Page 3. Right, so assume that our x belongs to R. That means that there's a number line and all the data points are on this. Okay, and let's assume that H is intervals on this number line. So one possible H could be 0.4 and 0.6. What that means is that it will call anything that is between this as positive and anything outside as negative, right? So what this means is that if x, any x belongs to H or is inside H, then H of x is +1, else H of x is -1. So let's say this is our hypothesis space. Now we want to see if this hypothesis space shatters a given subset. Okay, so let's say our subset is S is just one value, 3.4. It just contains one value, right? So let's say 3.4 is here. Now how many ways can we color this in? Two, right? We can either call it positive or call it negative, right? So let's say we call it positive, then we can always come up with one hypothesis which will also have the same effect, right? So good. And if we color it negative, we can always come up with the hypothesis anywhere which will also correctly color it, which means that this H shatters this S. All right, any questions? Now we expand it. We say, let's say S is 3.4 and 4.7. So 3.4 is here and let's say 4.7 is here. Now we can color this in four ways, right? So one is we call both of them positive. We can certainly come up with a hypothesis like this which will correctly represent it. So that's good. Call both of them negative, same effect, one positive. So let's say one positive, one negative, we can put it like this and so on, right? So it turns out that H will shatter this S as well. Let's call it S1 and this one S2, right? Now let's go bigger. So let's say it's 3.4, 4.7 and 6.8, which means that there are 3 points, 3.4, 4.7, 6.8. And now you can see where I'm going at, right? So if all of them are positive, of course we can put a hypothesis space like this or hypothesis like this. But what if two of them are positive and this is negative, right? Now you cannot find any hypothesis in your bag of hypothesis space which could correctly classify them, right? Because it has to include both of them and then this will get misclassified, right? So it turns out that H does not, let's call it S3, does not shatter S3, right? So the notion of VC dimension is that it tries to find the biggest subset that can be shattered by that hypothesis space, and that is the VC dimension of that hypothesis space. So if you think of it, what essentially it does is, so it kind of tells you the complexity, right? So for example, for lines, what will happen is, oh, let me actually define it. Right, so what does shattering signify? What it signifies is the complexity of a hypothesis space, even though it might be infinity. Is there a question? Oh, okay. Any questions? Okay. All right. If H does not shatter S, right? So let's say H is not able to shatter S, then that means that there could be a particular concept that partitions your S which would not be represented by your H, right? It would not be correctly classified by your H. So if your H is such that you can find many subsets, larger and larger subsets that can be perfectly shattered by H, that means that it can represent more and more and more complex problems, right? So that kind of is the notion why we look at H. So right, so then we define the VC dimension. So the VC dimension for any hypothesis space is the largest subset of H, or actually it's the size of the largest subset of H that can be shattered by this hypothesis space. Did I say H? Sorry. The size of the largest subset of X, which is your data, that can be shattered by H. So for example, we can look at lines, just for example, because we're talking about perceptrons, right? So let's say our H is all lines. Then actually we did that, right? So we can find a subset of 2 points, and however we color it, we can always find a line that will correctly classify it. We can go till 3, but we can't go beyond 3. Beyond 3, you will never find a subset that can be correctly classified, right? Now one thing you should remember is that even for 3, right, let's say your points are like this, they are actually on a line. For this subset might not be shattered by this H, right? Because if I color this positive, positive and negative, you can't draw a line that will perfectly classify it, right? But that does not mean that the VC dimension of lines of this hypothesis space cannot be 3, because remember the definition of VC dimension is there should be at least one subset. If you can find any subset of a certain size that can be shattered, then you call that as the VC dimension. Okay, so this is not possible, but you can always find another subset like this, and this will be shattered by your this hypothesis space, right? So in general, VC dimension of any hyperplane, so if your H is a hyperplane in d-dimensional space, if it is in Rd, right, then VC dimension of that H will actually be d plus 1. Okay, so if it is in 2-dimensional space, VC dimension will be 3, 3-dimensional space will be 4, and so on. So that's one way of understanding it. Okay, any questions so far? Yes.
Just in terms of pattern here, if you have a parameterized model, is the VC dimension always bounded above by the number of parameters in the model?
The number.
Since you have like intervals A, B, you have 2 parameters.
Right.
VC dimension is 2. You have hyperplanes, but essentially there's like D plus 1.
Right.
Parameters, if you include plus and minus, which sign it goes on, the VC dimension is D plus 1. You have. It just seems that the number of parameters in the model, VC dimension.
It could be. I've never looked at it that way, but yeah. So let's say our H is circles, right? Circles. Then which means that anything that's inside a circle is positive and otherwise negative. Then we can see what happens, right? So let's say I have 2 points. I can always draw a circle that calls them 3 points. I suppose you can still draw a. You should do it, right? 4, I guess maybe, right? You could still do it.
No, if you had like one in the middle and three around it.
No, but what I'm saying is you need to have just at least one subset. So you can always come up with one subset that would be shattered by circles, right? Or is that not true?
It has to be inside the circle. It depends on if you include the sign, whether the circle is like.
Yeah, you're right.
Be like another parameter.
Right.
Or parameter model, which again enables to shatter.
Yeah, you're right. So it could be. So the question that Adam posed was that it seems like however number of parameters are there in H, that the VC dimension seems to be that plus 1. And I can't guarantee that. It seems to be okay, but I'll check that, right? And in fact, I'm going to go to another result just now to see that as well. Okay, so where was I? Right. So now we can come up with VC dimension, right? But the question is, how can I use that to bound my M, right? Remember there was a result like this earlier, which is this. Oh, well, not this one, right? For if your data is in hypothesis space and a concept belongs to hypothesis space, then it's bounded like this. But the reason we went to VC dimension was that this is infinity for many cases. So how can we come up with the same expression for this? And again, I won't go into the derivation here, but this is the expression. Okay, so what happens is it looks very much like this, but some of the constants change. So it's not like you just replace it. You have to go through this whole derivation. So there's a book by Vapnik, Statistical Learning Theory, where he goes into all of this derivation as well. But the idea is that your M is now bounded by a quantity which is a function of your epsilon, your delta, and the VC dimension. So instead of H, which we used earlier, we replace it by the VC dimension of H, and then some constants change as well. But the general relationships are still the same, that if your epsilon increases, then your M will go down. If your delta increases, M will go down. If your VC dimension increases, M will go up. Because VC dimension is some notion of the complexity, right? So if you think about perceptrons, so if you're trying to learn a perceptron in two-dimensional space, then VC dimension will be something. But if your space becomes larger, so now you're looking at three-dimensional space, now you will need more data. So as your complexity of your problem increases, right? If you think of dimensionality as one measure of complexity, then you will need more and more and more data. Okay, so in fact you can go here and you can plug this equation and find the bounds for M here, and you will see that the bounds are actually pretty large. So these are bounds, right? All it says is that M has to be greater than this, but you might find a smaller data set that would still work. This is just the absolute upper bound that you need to have. All right, any questions so far? Yes, go ahead.
Actually, follow question on the interval example. We say the hypothesis does not shatter at 3, right?
Right.
But still, we can find one subset of set 3.
Can you?
Subset, yeah.
Which one?
Like, with all
All?
Yeah.
No.
So you count out all parts to satisfy at least one example.
No. So it has. So maybe I confused you a little bit. Basically, the idea is that to define VC dimension, you have to find at least one subset that is shattered. See, shattering means that every possible labeling needs to be represented by your one hypothesis in the hypothesis space. Right? So for this example, any particular three, on this number line, any points that you put, they have to be like this, right? So there will be one labeling always that will not be represented by H. Right? Do you agree with that part? Right? So which means that this subset will not get shattered by H. Right? And what you can show is that you will never find a subset of 3 points that will be shattered by this H. Because once you find the subset, you need to make sure that every possible labeling is represented by one of the hypotheses. All right, so one thing that might be on your mind, I don't know, is what is the VC dimension of a neural network, right? And it turns out that it's not very easy to compute that, right? Because a neural network is pretty complex. But what has been shown is that if you simplify your neural network, if you assume that in your neural network you only have nodes and there is no sigmoid unit, so you can think of it as a a linear neural network where the activation is just a linear value, so it's just bunch of perceptrons just added together, then you can compute the VC, or at least a bound on the VC dimension. You can say that the VC dimension is this expression. So it's 2 times the number of inputs going into each perceptron unit times S. S is the total number of perceptrons you have in your whole thing, times log of, this is just the natural exponent, times S again. So it's a function of the, so you can think of this as the complexity of the neural network, right? So if you increase the number of units, then this will increase, right? So of course, one of you might go ahead and compute the VC dimension of an actual neural network, right, with sigmoid activation. That will be fantastic. But so far, this is what we have. So this kind of gives you some notion. What it says is that, okay, if you keep increasing the number of neural units, right, then your VC dimension will keep increasing, which means that you will need more and more data to ensure that this your solution is pack learnable, which means that it makes less than epsilon mistakes 1 minus delta times. All right, so that is the relation. Any questions? All right, okay. So this time we are really finished with part A, because yeah, there's nothing beyond that. So I'm not done yet, of course, but let me, well, I don't want to start with the new part. So any other questions that you have? I want to make a few announcements before you go. So of course the assignment is due on Wednesday, so make sure you're on top of that. I'm still very nervous because I don't see too much activity. So either you have all just finished it or haven't started. So please do that, because it might take longer. Okay. Some tips about the assignment are that if you do a plain vanilla implementation with, you just follow what is there in the assignment description, right, you might be able to come up with that pretty soon with a solution. But what you will find is that it's very slow, okay, because for loops in Python tend to slow things down, especially when you have so much data, right? So you have to cycle through all of your training examples. So try to use some of the Python library, not libraries, but Python routines, so NumPy routines, to do your loops. Okay, so for example, if you have to multiply two vectors, right? So you have to compute W transpose X, right? One way to do it in Python is you do for I equal to 1 through length Wi times Xi and add it up, right? Another way to do it is just do np dot dot, which is a matrix multiplier thing, and just do W dot transpose comma X. So this is going to do it very fast. Okay, so try to do that, and then what you will see later on is that even if you have to compute matrix calculations, trying to use np dot dot will be much faster than doing something else, right? The same thing if you have two matrices X and Y and you have to compute the difference, instead of actually computing the pairwise differences, just use X minus Y in NumPy, right? So it will still work. So try to avoid for loops as much as you can, and you will, what you'll see is your codes will run much faster. Another thing is that when you compute the gradient, if there is any error in the gradient, that means that your gradient does not match your objective function, then what you will see is either your algorithm will quickly converge, your minimize routine will converge, and it will not give you a good value, right? So if you are getting accuracies of 9%, 10%, that means that your gradient was not computed correctly. So make sure that your gradient is correct, and one way to check that is that when you call your minimize routine, right, in your NN obj val, try to print out your objective function. So what will happen is that when the minimize function is doing gradient descent, every time it will call your objective function, right? So every time if you print your objective function, what should happen is, if everything is correct, your objective function should keep going down, because this is the error, right? So it should, every step when it is doing this gradient step, it should move towards the minima, which means that it should always keep improving. So if your objective function is not going down smoothly, if it is going all over the place, then there is something wrong. All right, so those are the things you can check to make sure that things are going well. Another thing I did was that I added a smaller data set, a small sample, so that you can run your algorithm on a smaller sample. It will take faster, so you can use that to debug. But when you submit your code, please first run it on the entire data set, the full data set. Any questions? Okay, so go ahead.
I just had a question on the pickle file, the format of the pickle file.
Right.
I mean, you've got like various variables to be added. Is it like a dictionary where you have like, those variables are keys, or is it?
You're talking about the pickle file that needs to be submitted, right?
Yeah.
Oh, yeah. I think it's going to be just a list, but I thought I asked the TA to post the order in which. In fact, what the TA will do is he'll post the actual pickle command, the save command, so you can just copy it. So yeah, that'll ensure that everyone has it in the same list. Yeah, thank you. Yeah. Anything else? All right, so we are done. Let's talk on Friday. Bye.